Good afternoon, everyone, and thank you for being here today. My name is Maria Pantopoulou, and today I'm going to present to you our work based on machine learning-based monitoring of liquid sodium vessel heater zones. First of all, I would like to acknowledge the other members that contributed to this work. Derek Halpin from Argonne National Lab, who provided us the dataset for this work, my supervisor from Purdue University, Professor Lefteris Tsoukalas, and my supervisor from Argonne National Lab, Dr. Alexandra Haifels. So I'll start the presentation by talking about the motivation of the specific work and why it is important to achieve early failure detection in several components of advanced reactors using remote monitoring. Then I will talk about the two models that we developed to solve this problem, a long short-term memory network and a gated recurrent unit network. Then I will present to you the results for the performance of the two models, and I'll close the presentation with some conclusions and ideas for future work. So some of the advanced small modular reactors, which are promising options for the future of nuclear energy, such as the sodium fast reactors and molten salt cooled reactors, operate at really high temperatures of several hundred Celsius degrees in order to achieve efficient thermal to electric energy conversion. These kind of reactors use ambient pressure liquid sodium and liquid salt fluids with melting temperatures of approximately 100 Celsius and 415 Celsius degrees. In order to prevent fluid freezing, there are heaters and thermal insulation installed in many of the components of these reactors. It is very important to be able to monitor these heaters and to be able to detect early failure with the greatest goal to be to achieve low operation and maintenance costs. So in all the heater zones, we have thermocouples, which are sensors that measure the temperature in the place where they're located. And using on-light remote monitoring and prediction of these sensors, we are able to early detect any sensor failures and then replace them. As I said before, it's very important to be able to have continuous monitoring of these sensor readings to detect any abnormalities in the sensor operation. So a way to achieve this is by using machine learning algorithms. However, when we use machine learning algorithms to predict future values, there is the problem of complexity in the dependence of the input variables. We all know about recurrent neural networks. We can use them to predict future values, but they suffer from the vanishing gradient problem. So a way to overcome this problem is by using similar neural networks, such as the long short-term memory networks and gated recurrent unit networks. So this is what we are trying to do in this work. We use these two networks and benchmark their performance. So for this work, we got a dataset from an experiment that was conducted in mental facility in Argonne during the sodium filling transient. And what we are trying to do is to predict heater zone thermocouple time series of an argon cover gas valve in a liquid sodium vessel. So we developed a stacked LSTM model and a GRU model. But before talking about the development of the two models, I want to talk a bit about the facility. So in the first figure, you see a schematic of mental facility, which is an intermediate scale liquid sodium experimental facility in Argonne with piping and vessel system filled with R-grade sodium. So the facility has 4 test vessels, many sensors, pipes, expansion tanks, and they are all interconnected via piping and tubing. The system is designed to handle both static and fluid sodium, and this actually gives us the opportunity to conduct many experiments regarding the needs. All piping, test vessels, tanks are equipped with heaters and thermal insulation in order to prevent fluid freezing and to keep the temperature of the sodium between a room temperature and a minimum to 1000 degrees Fahrenheit. Here in the second figure, it's like we zoom in one of the 4 test vessels. This is vessel 1 in the facility, and this is the vessel where we got our data from. However, the image you see here is before the heaters installation. So the experiment that was conducted lasted 3 days, and here in this figure you see a schematic of the vessel along with the connections and the orientations of the connections. So as you see, every vessel has dedicated lines for supply, return, drain, and additionally, there is an argon cover gas supply line at the top, and also a vent which is connected to a vapor trap. The overflow line is used to control the sodium levels in the vessel, whereas the argon cover gas is used to maintain an inert environment above the liquid sodium. Now, I'm going to talk a bit more about the argon cover gas because it's the one we focus here. It's used to display sodium from the system to achieve rapid draining and also to regulate and control the test loop pressure. So here you see the same schematic, however we have circled that valve there. So this is an 180 degrees auto valve in the argon cover gas supply line of this vessel. On this valve, a thermocouple is installed, and this is where we get our measurements from. So as I said before, the experiment lasted 3 days, and the resolution of our measurements is 1 second. So in total, our dataset consisted of 225,500 readings, and these readings were from this valve here. These measurements were taken using a K-type process control thermocouple. K-type process control thermocouples are often used because they have fast response, they are inexpensive, small in size, and very reliable. So another thing that I want to mention here is the thermocouple measurement uncertainty. So for this experiment, the process control thermocouple measurement uncertainty was plus minus 1.5 Celsius. And I mentioned this number because then I want to compare this number with the error in our predictions. Now I'm going to briefly talk about the two models. So here you can see an LSTM cell. So this cell consists of 3 main gates: the forget gate, input gate, and output gate. So the forget gate decides which information needs attention and which can be ignored. The input gate decides what relevant information can be added from the current step, whereas the output gate determines what the next state will be. So as you can see, there are 3 gates, and this makes this cell a bit more complex. However, in the literature it's mentioned that when we have a large data set, LSTM can give us good results. Here you see the structure of a GRU cell. Looks similar, however, this cell has only 2 gates, an update gate and a reset gate. So the update gate determines the amount of information from previous time steps that needs to be passed along to the next state. And the reset gate decides the amount of past information that needs to be forgotten. So as you can see, this cell is much simpler than the LSTM cell. And in the literature it's mentioned that GRU models, when we have a small data set, can perform really well compared to LSTMs. And also their training and prediction time is much better. So now I'm going to talk about the parameters of the models that we developed. First of all, I want to say that all these parameters were exactly the same for the 2 models because we actually wanted to do a comparison using the same parameters. And we first did a hyperparameter tuning to decide these parameters. So we split our data set 65% for training, 15% for validation, and 20% for testing. And we used the segment with the highest temperature values to be the testing part. Regarding the LSTM model, we decided to develop a stacked LSTM with 2 LSTM layers. After every LSTM and GRU layer, we also added a dropout layer with dropout rate of 20% in order to avoid overfitting phenomena and also to get better results. In every layer, there were 15 hidden neurons. And here you can see 2 formulas for the root mean square error and the maximum absolute error. And these are the 2 performance metrics we use to evaluate the performance of the 2 models. So here you can see the training and validation loss versus epoch curves for both the models. So for the first one, the stacked LSTM, actually I want first to say that we trained both models for 50 epochs. And as you can see, we needed to reduce the learning rate to this number here. I think the default number for the learning rate, the item optimizer, is 0.001. However, when we use this number, our curves didn't look like they had a good fit. So either we had overfitting or underfitting. So we needed to change this number, and the result is this one here. So, as you can see, both gears look like we have a good fit, and we can understand this because, first of all, we see the training curve, the training loss curve, which is the red one, to decrease over time and finally reaches a point of stability. And the same happens with the blue curve, which is the validation loss. And we also see that there is a small gap between them. Also, when we see these two graphs, we are able to see that both of them from the beginning had very small loss. But when we see the y-axis of the two graphs, we see that the GRU model performed a bit better. So, in this slide you see the predictions of the two models. As you can see, I have also put the two performance matrix. So as you can see, the red points are the real data, whereas the blue points are the predictions of the models. Both models performed really well. However, we can see that in the Stactal STM model, we are able to see the blue points, which are the predictions. And that means we didn't have the exact values as the real data. Whereas in the GRU model, the blue points cannot be seen. And that means that the predictions were really close to the real data. However, if we check the performance matrix, they are really good for both of the models, with the GRU model being better than the Stactal STM. So now I also put here what I told you before about the thermocouple measurement uncertainty, which is plus minus 1.5 Celsius degrees, because now we can compare this number with the two performance matrix values. And we see that for both of our models, they are much lower than this value of the uncertainty. And that means we can actually use both models to predict future values of the thermocouple. So to conclude, in this presentation, for this work, we used a data set obtained from a process control thermocouple of a valve heater zone in a vessel during the sodium filling transient. And we benchmarked the time series prediction using two models, a Stactal STM and the GRU model. In the results, we saw that both models predict the time series really well, and the two performance metrics, the RMSE value and the maximum absolute air value, were much lower than the thermocouple measurement uncertainty. However, it was obvious that the GRU model performed slightly better than Stactal STM. Now, our ideas for future work is actually to see what other machine learning algorithms we can use, like ARIMA and also Bayesian, and also to perform forecasting of different transient data sets from the mental operation. This work was supported by the ARPA by Gemini program and the donation to AI Systems Lab at Purdue University by Goldman Sachs gives, and also experimental data was obtained from the mental facility in Argonne. That was my presentation. Thank you for your attention, and if you have any questions, I'm happy to answer.
So was your testing data and training data from the same time series?
Yes.
Okay.
I just selected the testing data was the last part, and the last part had the highest temperature values of the data set.
As in the last?
Yes.
Like 10%?
Yes.
Okay.
I have two questions. So the first one, how do you see this is practical? So what's the practical implementation of trying to predict, for example, time series? So where do you see this is useful from a practical aspect?
In this way, we can detect if there are any abnormalities in the sensors, because I mean, if we see that finally the sensor gives us a weird value that we don't expect and we have already predicted it, we can understand that something has happened there. So we can then replace this sensor early.
The second part is usually for STMs, you try to do kind of a transformation of the data, or like a look back window where you use previous time steps to predict like the future. Did you do this type of transformation for this model or no?
No, it was just, the LSTM was just one step ahead. I didn't do any other process.
Thank you.
You're welcome.
Other questions? I don't know whether I missed the information. So you showed some uncertainty of the models. So what kind of uncertainty is that? It's like epistemic or aleatoric? It's like the model uncertainty or the input uncertainty? What kind of uncertainty is like, or it's composite uncertainty?
Yeah, I'm not sure about this because I saw this number from the mental facility report and they reported there. But probably it's electronic or something like that, but I'm not sure to answer. I can check it. Okay.
Yeah, so I also was curious about that uncertainty issue. So it seems like, okay, so this is good at predicting what a stack of numbers would predict. But is it important to know what the actual temperature is? If so, I mean, you do have to do an uncertainty analysis that goes into where are you getting those numbers from? Because there's a lot of uncertainties in the sensing, scaling, the installation of the thermocouple, the A to B conversion that goes to the data story. There's a whole lot of stuff that's uncertain that affects the actual number. So is this useful in predicting the actual value that it should be versus the performance of the thermocouple?
So your question is why it is important to do that?
Is it more important for the purpose of detecting a failed thermocouple versus knowing what the value should be in the process line at any future point?
Yeah, I think it can be used for both.
Okay, so, but I see that there's a large uncertainty that could be between the readings that you've computed as a predicted value and the actual value that it hasn't been addressed.
Actually, the difference, I don't think it was that much because if you see the y-axis, it's like very small, the range for predictions. I mean, that's why I said even stacked LSTM didn't give us bad results because if you see the y-axis, the difference, the numbers are small, 0 point something.
So I guess I'm saying, so it's important to know to a certain threshold what the uncertainty is.
Yes.
Beyond that, it's not as important.
Yes, because if we see something very different than that, we can say that there is an abnormality or something, or the sensor is
For
failing.
the sensor.
Yes.
Thank you.
We have time for one last question if anyone has a question. All right, so we'll go ahead and thank our speaker again.